All right. Hello, everyone. Today is the day number 2 for trying to get a board put together. So, hello, everyone. We worked yesterday on the fx2 logic analyzer schematic, and today we will continue on that. I have posted the work we have done yesterday on GitHub. You should be able to find it there. It's on GitHub, Esden, and then fx2grok, and then it's in the branch flat. So you should be able to see it there. So if I switch over, so that's, you should be able to see it here. If you also look in the stream, you will see I have added the Gitter chat so that it is an overlay. And you should be able now to see also what is going on in the chat, even if you are watching it later. After the stream is already over. I have decreased the levels of audio a little bit because I realized that it was clipping quite a lot yesterday. So the audio should be a little bit better today. Okay. Otherwise, let me just check that the stream is running as it should. It says it is live, but it is not showing me the preview at the moment. But there we go. I think not now. Escape. There we go. YouTube is being very difficult with their user interface. It's trying to full screen everything. All right, that looks better. Okay, so this is the GitHub repository, and I have a few additions for the schematic that I would like to be working on. So this is the exported stuff. For an overview, we have added the fx2, we have added some input protection, we have USB, and we have power supply, and we have a crystal. I had some questions yesterday why, for example, the 5 volts are connected to the protection circuitry of the USB interface. And it is there. So the interesting thing is it is actually also protecting if you zap the USB connector on the VCC input. What happens then is this Zener diode that is in the very center. Zener diodes are interesting diodes that also conduct in reverse if you reach the Zener voltage. And so when the voltage goes over 6 volts, it will conduct in reverse, so it will shunt the over voltage to ground. So this is there to protect also the 5 volt line. That's why it is also connected to 5 volts. I was thinking about 3.3 volts, and someone mentioned that this wouldn't be good for the linear voltage regulator, which this is not really true because we still have the Zener diode in there, so it would still shunt it to ground. But this is the correct way of using it, having it connected to 5 volts. The other diodes are there to clamp it so that the voltage doesn't go below 0 and not above 5 volts, and it conducts and it shunts it here, even if it is below the 6 volts reverse, so the Zener voltage of the middle diode. So that's that. We can look it up in the datasheet. These things are always listed. So if you look here, this is the datasheet of the 4-channel, I think, that we are using. Let me check. Yeah, this is the 4-channel protection circuit. And this one is connected to, at the moment, I think I have it connected to 3.3 volts. Let's see. Yeah, currently it is connected to 3.3 volts. If we had, for example, a dual supply transceiver between the GPIO here, the PBs, and the output, this is what we, for example, do in the Blackmagic probe to support the down to 1.8 volt targets, then we would need an additional pin here on the connector to provide reference voltage. I was thinking about adding that here, but I think this will overcomplicate things and make it a little bit less usable. We would need to add some firmware options inside the fx2 firmware from Sigrok that would allow also target voltage supply switching as we have it on the Blackmagic probe. It would require quite a lot of additional rejigging so that it is as useful as, for example, the Blackmagic probe. Not having the target voltage supply available makes things more complicated because you have to always make sure that you supply reference voltage from the target. Yeah, anyways, I decided not to do that. What we could do here on the protection circuitry, we could theoretically connect it to the 5 volts of the USB voltage. I don't know how much that makes sense. This will basically shunt if it is below 6 volts and it is above 3.3 volts, it will basically try to put it into the 3 volt rail. So probably we should put it on the 5 volt stuff instead. It's probably safer than trying to drive the linear voltage regulator to 5 volts and it has to compensate for that. Driving linear voltage regulators in reverse, it should be okay, but it's probably not a good idea. So I think the first thing would be to change that. Now that I walk you through this, I think it is a good idea to have the 5 volts here. So let's do that. Let's delete and move. Okay, so let's have that on 5 volts. So that's one. Then the other thing I did was looking at other schematics from other probes. And one more thing that I found on there, I'm not sure this will be visible. Let me switch this over like this. There we go. And then, yeah, I was waiting for the lag of the video monitoring. Oh, thanks. Thanks, Uwe. It's good to know that the audio is good. Okay, so the pull-up resistors is something I would like to add. Then we have just a capacitor here. So if you look at the shunting here, the shunting is using separate diodes. They are also doing the same thing as we have in the integrated part. Then there is here one diode. I think they meant to designate it as a Zener, but I think this is just a reverse engineered schematic, so it is not very clear. And then there is a capacitor too. I think we have already capacitors because we have it on the input of the voltage regulator. We already have the 4.7 micro capacitor, so I don't think we need that. Okay, so going back, I think we should add the pull-up resistors because this way we have a defined status of the lines if they are not connected to a target. And they should be high-value resistors to not require a lot of drive from the target to overpower those pull-up resistors. So I think maybe something like 100K should be good enough. But then also you have a defined status so that when the logic analyzer reads the data out, it will not have like a jiggling output because it is in an undefined state. So Let's do that. Copy this, and we create basically a pull-up structure here and call that 100K. And let's copy this, copy how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Now let's wire it up. Yeah, so I think this is from the perspective of the target interface, that would be the last thing to add. And let's copy this. This should be pulled up to 3.3 volts, I think. Because now, should it now? Because, well, it's 100K, so it is quite a high resistance connection. So even if we drive 5 volts on here, it should be fine, because the current that this will draw will be quite small. Oh, let's just do that. Unless someone has a good comment that I should change things here. All right, then, oh, this is stupid. What am I doing? So this should go to the interfaces. So let's just delete this. This is stupid, of course. Let's do that. Should we pull it up before or after the resistors? So in this schematic, it's after the resistors, or whichever direction you're looking at it. Oh, so the interesting thing is, look, if I just drag it, it will pull off all the traces. What you do, you press tab, and this will keep the components attached to the schematic. That's very useful to know. I did not know that at the beginning. It was quite annoying. So there we go. So let's move this guy also. Will this fit? Just about. Yeah, just about. Let's move this guy away a little bit. Tab. Yeah, it's out of the way. Alrighty, wire. Okay, so now we can move this back because we don't need that much space. There we go. Now let's annotate it and see if the resistors worked. Okay, we have R8 and R9. They are all here. Good. Now, if we look at so the next thing is the flash chip. So we're missing the flash chip. I looked at flash chips, so memory. In the datasheet of the Cypress chip, they recommend using the microchip technology 24LC I2C flash chips, or EEPROMs. I think we should just stick to that. It will make things easier. And I also looked at the guide. Let's see, EEPROM. Let's see if the table is in here. I don't remember exactly which one of the documents contained the table of different EEPROMs you can use. Because there are two things you can do with an EEPROM. You can either load or either not have the EEPROM at all, then it will use internally default vid and PID, as well as configuration bits. Or you can have an EEPROM that has wrong data in it, then it will ignore it. It looks at the first byte of the EEPROM to decide if it should just load the vid, PID, and the config, or it should load the vid, PID, config, and the RAM content for the microcontroller. So the microcontroller does not have internal flash that it runs from. It only has RAM, and if you want to preload a firmware to it, you have to use the EEPROM. There we go. Okay, so I found it. So EEPROM bootload data formats. No EEPROM or EEPROM with invalid boot data. So let me make this a little bit larger. It should be better visible. Okay, there we go. And then it will not do anything, and just use the vendor Cypress Semiconductor and Easy USB FX2LP for the product ID. And then depending on the chip version, it will set the chip revision and data about it. I'm not exactly sure where you can read it out. Probably through the USB interface, I would assume. The other chip, so the other setup is having C0 in the first byte. Then it will load VID, PID, and DID, and so device ID. And then C2 would be load firmware to the chip RAM. So on the startup, it will load a firmware from there. Because we are using it with Sigrok, the default behavior of Sigrok is to load a firmware anyways to RAM through the USB interface. So we don't need to keep a firmware on this chip. This also tells us what size of a chip to use. So in the C0 load, in the EEPROM address, you have this structure. So this is only 8 bytes of information that we need. We need the vendor ID, product ID, and so on. So we can use the smallest EEPROM chip. And I'm trying to find, because there was also a table that showed us how to deselect the EEPROMs. There was somewhere an information that you can select an address or something like that, and then it will decide which size of the chip it is, but I can't find it at the moment. Anyways, doesn't matter. For the circuitry, all we need is to find the right chip. And I looked here. These are the 24LC00 chips. They have 128 bits of data. So this is 16 bytes of data in the EEPROM. That's all we need. This is more than we actually need because we need only 8. So we can just use this. And you see here on DigiKey, I also sorted it by price. So this chip is the same price as the 1 kilobyte chip, or kilobit chip. So this is 128 bytes. It's still not enough to store the RAM content, because RAM content is, I think, 16 kilobytes or something. So we will not do that. There is no point. These chips come in an SOT23-5 package, and the datasheet, there we go. This is the datasheet. There are also versions of it in a DFN package, so we could theoretically make it nice and tight. For now, let's just drop in this this chip with the SOT23 in there. Yeah. So now, if I go into the schematic, there's the schematic. If I wanted to use the standard library schematic symbol, we could go 25 LC EEPROM. That's close, but it's not exactly what we need, because this one has 8 pins that have stuff on it. Then let's see, is there any one of them that is basically the right symbol that we can just copy over? SCL, SDA, NC. Let's look. Yes, so this is NC. So SCL is pin 1. Oh, come on. SCL is pin 1. Pin 3 is SDA. pin 4, pin 2. So NC is 5, NC is 5. Oh, so this is reversed. This is wrong. We have to make a new symbol no matter what. 24AA or 24LC is below this. LC01. So there are some LCs, but they are all the larger pin count LCs. Okay. You know what? Let's just take this guy and create a new symbol. So we will go in here. This is the symbol we made yesterday. Yeah, let's just put it in the pkl-misc. There's no point for now, but we have to go and download it from a different library. What was the library that we were looking at? EEPROM, so it is memory library. Memory library. Yeah, so this is pkl-misc only. So let's open a different library. Memory. Oh, I do have a pkl memory, so we will drop it in there. Okay. Okay. 24LC. Yeah, this is close enough. We will just rejig the numbering of the pins. And call it correctly with the right amount of memory. So let's make a copy of this. So it is 24LC, 24LC 00. So the part that has 2.5 volts to 5.5 volts range. We could use also the 1.81. It doesn't really matter much. We could use either. Okay. LC00, because that's the 128-bit version. Okay. Existing entry in the component library memory. Do you wish to replace the current component in the library with this one? Not really. Let's switch libraries then. pkl memory. pkl memory. Okay. And then make a copy. LC 00. That's better. SOT23, description, 128 bit, I2C, I2C prom. We can also set this link to the datasheet, datasheet options. Okay, description, that's correct. Oh, yes. All right. So what is going on here? Why does it have... Oh, because it is preset. I see. Interesting. Yeah, well, you can preset it also in the library. And let's just delete this. Although we could assign the footprint and just assign it from our SOT library. 23-5. There we go. Okay. And we need to change the pin numbering, right? So it is SCL, VSS, SDA, SCL, VSS, VSS, yes. And that's pretty much ground. Then SDA is 3. Then we have 4 is NC. So this will be 5. 5. And NC will be 4. And I hate hidden pins. This is a bad thing to happen because you could just put a line on the schematic and it would connect it. It's a bad thing to do. Don't hide pins, just call it NC and make a cross on it. Make it visible. Okay. pkl memory, yes, and memory lib, yes, so that's saved. Okay, now we can add it to the schematic. In the meantime, I did set up Git correctly, but I will do that offline. There's no need for me to do these things on the stream. Okay, and let's put a new prom here. PKL memory. There you go. And why? What is going on here? What am I doing? Why is it PKL memory? There we go. That's correct. Oh, oh, of course. So that's a quirk of the current version of KiCad. Because this name exists in a library that is in that list earlier, it overrides my library. So that's why some, but not all, which is a mistake, I should fix that, of the symbols have PKL underscore prefix on them, because otherwise it overwrites things. This will change the nightly builds, and Wayne Stumberg is fixing that stuff, and it will be fine. It will work well. But at the moment, it is clashing, and you have namespace pollution, because there is no prefix which library that symbol came from. So let's see. I cannot rename. I have to probably make a alias. No, cancel. Can I rename this over here? Yeah, I can't. So preferences, edit. Yeah, I don't think I can do that. So let's do this like that. PKL as a prefix. Okay. Move this guy a little bit further. Let's change the grid. 50, move. There we go. There we go. Save this. And we can go and load, delete this guy from the library. Okay, and this is now should work. Okay. Let's load this. PKL memory. There we go. So it is loading it correctly and not clashing, namespace clashing. What we can also do, let's mirror that guy. Orient component, mirror vertically. Because, so power should probably go over here. That's a better spot for it. Actually, it should go here somewhere. Because crystal is on top, power should be, I will reorganize and clean it up, the schematic a little bit more later, after we have everything here, because I like clean schematics, but let's not do that for now. And power and this, and we don't need to we can leave the unconnected, and we will copy 3.3 volts, that's supply, ground, and now we need SCL and SDA. Okay, and footprint is already set. Good, so that's done. Then we can fix also the footprint for the connector, because I didn't want a through-hole connector. I wanted an SMD connector so that it is nice and easy to use. or assemble actually. That's what I meant to say. And we do some tech, and we use double vertical. That's the correct footprint. Okay, so now that is updated. So we can generate the netlist. So one thing I will do is just delete the stuff here and just delete it because we don't need it. We will update it anyways. And yeah, just create the netlist. I think we are actually done with the schematic itself. I don't think we need anything else besides what we have on here. This would be a nice basic with protection circuitry for the FX2. Oh, one thing that I forgot to mention. Uwe did an amazing job of updating the wiki for the fx2. So the fx2grok now got a new nice table that Uwe put together to compare the 3 versions of the hardware. So Uwe made the fx2grok tiny, and this is small, and it's designed by him. It uses also CC by SA. It is double-sided 2-layer PCB. So components on both sides, and so on and so forth. So this is very useful to see what the features are of that board. Then he also added his current project of making it even smaller than the 13 by 13 millimeter board using a BGA version of the FX2 chip, which is pretty amazing. I'm really looking forward to see that. It's like, good luck. It will be awesome. Then we have the fx2grok flat. This is the version I'm working on. It will have the components only on one side, and it will use a very similar design to the fx2 tiny, but have additional protection, input protection circuitry and stuff like that. Another thing is I try to make it easy to machine assemble, because I have a pick and place machine. So it would be nice if it would be also easy to pick and place. Because of that, that's the reason why I prefer using the footprints that are OSMD. That's why I put everything on one side, because then I can only pass it through the pick and place machine once, assemble all the stuff, put it in the reflow oven, and it's done. I don't like through-hole components because that requires either manual soldering or an additional machine that is like selective soldering machine. If you are interested what that is, it's like Adafruit has one of them. It's pretty awesome tool to have in the shop, but our operation here is not big enough to afford tools like this. Anyway, so that's why there's no through-hole components on here. Yeah. All right, so I made the net export. Now I can import it into the board. So, oh, one more thing we can do before we do this is actually do some electrical rules checks. So let's just run it and see what it is complaining about. It's complaining that the pin connected to some other pins, but no pin to drive it. So this is the power net, and this is the net 9. So which one is it? So this is the ground net. So ground net is not driven by any of the components. That means there is a workaround for this. In KiCad, you just put on one of the nets, it's like, let's assume that the USB connector is the driving source for the net. Then let's just add power flag. And this thing will basically tell, where do we put it? Let's just put it here next to the ground flag. There we go. So now it is, this thing will indicate that this net is driven from here. It just makes the ERC or electrical rules checker happy. So run, there we go, done, it's happy now. Everything else seems to be okay. So we don't have any unconnected nets or stuff like that. So let's show that. Let's remove this no connect. It should complain. Yep, there you go. It's complaining that this pin, where you see the arrow, is not connected to anything, and it is complaining about that. So we can now add the no connect back and run the ERC again, run, and now it is not complaining anymore. Very nice. Okay. Now that this is done and we have everything we want, we regenerate the net, generate, and save. And we go to the PCB board design and import the net. So read current netlist. So this looks good, no errors. Close. Now we have the blob as we saw yesterday. So now let's go to the legacy canvas and right click and spread and place, spread footprints, and that's done. Now let's switch back to the GAL mode and move this stuff. There we go. Okay, so I usually design my boards here in the corner. I don't know, it's just because the origin of the whole coordinate system in the design software is here in the left upper corner of the paper sheet. Just stay there. It's like if you look here at the bottom in the command line, you see the coordinates where you are. This is a useful thing to have because later on we will use that to reference things. And then you can press space and then reset the second coordinate system to make relative movements. So I like having the stuff aligned to the grid that is the normal grid, even though you can set the origin of the grid using this tool here on the right. Yeah, for now, don't worry about it. You will see how that looks like when we start laying out the board. So now let's look at the components. This looks pretty good. We have some components that have their labels on the silk screen. This is something we have to fix. And this is part of me cleaning up my my libraries. I should have them by default be on the fab layer. This is how I usually use that, because on the PCB, my PCBs are usually so small anyways that there's no space for labels on them anyways. So I rather have everything just by default be, instead on this silk screen layer, be on the fab layer that you can then use, just print out with your printer as a reference for how to populate the board. So let's move that. All right, so that's moved. The size of the board, this is another thing we should think about. So let me save this for now. We want the board to be like a lengthy, like a USB dongle size, so something similar to the Blackmagic Pro probably. So something along these lines. Let's see, like this. Let's see if it will focus. Switch. I can see what I'm doing here. There we go. Focus, focus. You can do it. Yeah, this is a dirty Blackmagic probe. This is the size, and this is it would be nice to have a logic analyzer of this size. You can throw it in your bag. The reason is, for example, I carry with me a sturdy hard disk, like USB hard disk case, and I throw in all my tools into this so I can travel with it. Yeah, it's like this, like me. Yeah, so this is my collection of stuff that I carry with me, including a Blackmagic probe and an autopilot and some prototypes and stuff that I like working on when I'm on the go. So having that case, I also like stuff that fits into that case. If you take this is quite large. This will not really fit in here. This is not nice. If you look at a JTAG programmer, that is like a normal size JTAG programmer, this is JLink, for example, again, a massive piece of kit. I like things small so that I can just add to this small box, have one box with all the tools I need when I'm on the run. There you go. So this would be one possible size. We can make it bigger, like the 1bitsy. This is also nice and small. So I think to make things easier for us, and we have already a bunch of circuitry on there, let's start with the size of the 1bitsy. So the sizes I could look up in the design files, but calipers for the win. 18 millimeters wide and 38 millimeters long. So let's make it 20 by 40 millimeters. That's nice. It's a 1:2 ratio. I don't need to put it so far away. There we go. So let's make this, yeah, tunnel effect. Let's see what is going on in the chat. Let me catch up with it. Yeah. Yeah, nothing. Okay. Okay. Just reload just to make sure that I'm seeing everything up to date. Oh, great. YouTube page is crashing. I hope the signal is still coming. All right. Is it live? Good. Okay. All right. Yeah, if you have any questions in between, you want me to show you something or explore something, just let me know. I'm happy to answer your questions. Okay, so let's create an outline. Oh, one thing we can do beforehand is go in layer setup. This thing will be a 4-layer board because I'm lazy. We don't need adhesives. We need courtyard adhesives. We can disable. We can disable these layers. Margin, I also never really use. It's the setback from the edge cuts. Yeah, drawings user and comments user. We don't need that. Okay, there we go. So that cleaned up the layer count on the right here. There we go. Edge cuts. Let's draw it. We want, let's see, on the bottom here. Oh, we can also set the design rules. Design rules just from the get-go. So traces 0.15 millimeters. That is, I think, 6 thou. Then the via diameter is 3. And via, no, wrong, it's 5. So we have an annular ring of 0.1 millimeters. Okay. And there we go. And the grid, we are in millimeter mode, that's good. We need to change grid 0.1, that's fine. So let's get away, make 20 millimeters from the edge here and 20 millimeters from the edge here, so that we have plenty of space. Let's create an outline, and this will be, oh yeah, we should do this as relative. So we start here, press space. Oh yeah, I didn't enable this time the preview. So what was it? Key screen key. Let's enable screen key. This way you should be able to see what I'm typing. There we go. Okay. So we were, where were we? 20 by 20, 20 by 20, enter. And now we can go to 30. That's what we said as a starting point, and then make it 20 millimeter, no, 15. Oh, right, it was 40? 40, right? Because it was 38 or something on here. Yes, 40 millimeters long. Sorry. 30, 30, 40. Yeah. And next, 20 millimeters long, wide, 16, 18, 19, 20. And this should go to 0. And 0. There we go. So we have a preliminary outline. Now we can put some parts. Move, rotate. What we can also do is add some reference lines. On the drawings user layer, we can add the middle of the board. So this would be 10 millimeters. Let's just add this. And there we go. Just to have a nice reference where the center of the board is, so that we don't get trigger someone with OCD. Move. And move. Yeah, I like everything set up nicely and neatly, like symmetrically or with good ratios. It makes me happy. It's a nice thing to do. We can move this guy. This will be roughly in the center. There we go. And then we can put this guy. This will be here, also in the center. Let's pull it back from the edge nicely. And yeah, so that's starting to look good. We can also disable the labels because there's no need for that for now. Oh, and then we see here that this guy needs to go on the other layer. Okay. Nice. So now that we know that the USB connector goes here, we can lock that, lock footprint, so that we don't move it by accident, and it would be quite annoying. I would like to check how far from the edge of the board I have the Blackmagic probe connector, because it is very tight to the edge if you look at it. So let's try to get that exactly the same. Let's save this and go here, file, open recent, Blackmagic probe, KiCad PCB. So to measure the distance, what we will do is the center of this guy is here. Mask, render, anchors. Where is the anchor of this? Yeah, the anchor is here. Oh, that's the easiest. I probably should just go here, go on the edge, reset the relative distance, and then move this guy, footprint, and then if I press move, the cursor will jump to the position. It's minus 3.8 millimeters. Okay, good to know. So in the corner here, in the bottom here, you see dx, so delta x and delta y, and the delta x was at minus 3.8 millimeters. So that's clear that it is its distance to the edge of the board is 3.8 millimeters. Okay, let's open our working project again. Exit without save. We don't want to save the changes. And this guy, move. Let's go on the edge, reset, and minus 3.8. 3.8. Bam. It's nice and tight. Okay. Let's move these guys too. So this one can be locked. Lock footprint, because we will not be moving this guy. And let's put this stuff on the board. Just roughly and lay it out. So crystal will be here. The good thing would be to figure out what roughly the distances are. So move. Let's see. Where is the USB interface? So maybe I should is that relative? Yeah, so this guy should be the data interface. 5 volts PB. No, this is the PB stuff. That's going here, so we should rotate this guy. Okay, so these are the outputs of the interface. So this is the GPIO we will be using. This guy is the USB protection circuit. Let's see. Yeah. There we go. So USB is connected here on the bottom. How many of the traces do we need? Should we put it at 45 degrees? That's my question. Might look cool. Not sure it's useful, but it would look cool. So roughly, so this is the SD. So this is the flash chip. This is the power supply, so let's have that here. Then we have a bunch of protection input resistors. One goes here, one goes here. So this guy is the pull-up resistor bank, and this guy is the other protection circuit. So 4 more. This will be interesting how we will route this, because we have PB, so these guys basically are like this. We would need to move this. So this is on the bottom. Okay. So these are, so PB0, PB1, PB2, PB3, PB4, PB5, PB6, PB7. So these are like this. Protection stuff, pull-ups. Okay. and there should be another pull-up bank. Pull-up bank. Pull-up bank. There we go. Okay. Then we have the LED. Let's see, there is also a resistor that belongs to the LED. Let's get it where it belongs. So that would be here. And this is nice, okay. So let's put it sideways. The nice thing about putting an LED sideways is it is illuminating to the side of the board too. Yeah, it's a thing. Okay. And then we have the 0603 capacitors. One goes here for the 5 volt, and then we have another here that goes for the 3.3 volt. Then we have the 10 nano that is belonging somewhere. Let's just select it. So we can go into the schematic. Schematic, I said. No. What did I do? I double clicked on the net. It's not what I meant to do. So we have the schematic and we want to find a part. We can just click on the part and then go into the PCB layout and the part will be selected. So there's a nice indication. If you have 2 monitors, it's even better because you can have the schematic on one monitor while you have the PCB layout on the other, making things even easier to handle. Okay. Then, so that's done. Now let's look at the different power supply decoupling capacitors. Or let's add the 12 pico to here and the 12 pico here. And then what else? We need the reset stuff. So the pull up here. And the pull up here. And the capacitor that belongs to that cluster here. Then we have the SCL and SDA resistors. This goes next to the EEPROM. And another one next to the EEPROM. Then we have what? We have this, so the LED is already on there. Let's add the 3.3 volts VCC decoupling capacitors. So that would be going to pin 11. Let's start with 11 on the left. So C1, which is this one, goes to 11. Rotate. So that's pin 11. Then we have C2 goes to 17. Uh, 17. Let's rotate it the other way. Oop. 17. Oh, this is PB already, so this will be tight in here. So let's put this guy like this. You want them to be as close to the power supply pins as possible, but it's not always a possibility. So we will have to route around here. Then 27 is the next one. 27. That's this corner. Then we have 32. 32. 31, 32. Very good. And we have 43. 43. That's this guy on the corner here. So wake up. This belongs basically here. This belongs to the 43 pad. And we have 55. 55. Okay, good. Now we can do also the AVCC stuff. This would be pin 3 and 7. So pin 3 gets at 2U2. Pin 7. And 100 nano. Pin 7. Nice and tight. Then 2U2 goes to, that was pin 7. Oh, I meant to put it on 3. Right. Okay, so these two guys go on pin 3. That will be fun. So this guy, there and there, pin 3. Good. Then we have this massive oscillator for crystal. Yeah, we might want to find something smaller than this. Yeah. Okay, so let's go back here. So now that would be the 7. There we go. And then C10. There we go. So that would be everything is pretty much on the board. So on the first glance, it looks pretty good. There's still a lot of space to do the routing. We probably will be able to even compress the size of this board, which will be nice. Yeah, so one more thing that we can add while we're already here. And because I think about it, we can add dimensions for those that are curious in the future how large the board is. So it is 40 millimeter long at the moment. It might change. And then we have the second here is 20 millimeters. There we go. Cool. Yeah, so I think we made some significant progress today. We moved the stuff forward, added a bunch of stuff to the PCB. We added the protection, so the pull-up resistors. We added the EEPROM. And we put the stuff onto the PCB. So let me look how long we are running here. We are running for an hour. It's like I think we have still time, so we can also continue doing some other stuff. But now I have to think. It's like this is the stuff I was planning to do for now. But we have to think what will be next. So besides trying to start routing this stuff, yeah, the biggest issue I have at the moment is that USB has to go all around here to the side. I don't really like that. I would prefer if it was USB was going on one side and the GPIOs on the other. But it doesn't mean we will be able to. What we can do is add the planes, which are pretty straightforward. So let's add polygons, the fill planes. Let's start. This will be on layer. Let's start with copper layer 1, and this will be here, and this will be ground. And I'm checking what the track widths are. The track widths are crazy. It's 0.25 millimeters. This is almost 10 mil thickness. This is crazy. Okay, let's change the design rules. Clearance is 0.15. Track width is also 0.15. Via diameter is 0.5. Drill is 0.3. Micro via, I don't care. I don't think we will use that. So let me set this. So 150. We might need thicker or wider traces for power later, and I can add them later to the design rules. Another thing is pads masks clearance. I think 0.05 is the usual thing that I use. And bam, things look much better. So you don't have this massive openings in this in the solder stop layer. Solder stop will otherwise expose, if you leave it so large, which is the default on in KiCad, this 0.25 or something crazy like that. Then very often if you have stuff that is reasonably together, and these are not crazy DRC rules that I'm following here, this is like a standard OSHPARC setup, then you can expose ground planes on around it and like have shorts and horrible stuff. So this is important thing to change. So you go on dimension and pad mask clearance. Very important. You need to adjust this. Otherwise you might be sad if you make the board. But you should be able to catch it if you review your Gerber files before you send it in to a PCB manufacturer. Okay, that's adjusted. Now let's add the plane as we started doing on ground layer, and corner, 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 and corner. Oop. And we can edit this. Let's adjust it so that it is nice and clean. And now press B. This will fill, and N clears it. So B, N, B, N. B fills the connections. So all the ground connections are already done on the top layer. Now we can create copies of this. I think it's D. No. So how was this? Duplicate. Control D. Control D. Enter. Edit. And let's move it on the bottom layer. So we have one on the bottom layer. Then zone outline. Control D. Enter. Edit. And let's put it on the in layer. Where do we want power? Do we want power on the higher layer or the lower layer? Let's just put ground here. Okay. Well, actually, I will make another copy. Hello. Control D. Why did it move? Edit. And we will move it to the inner layer there and change the net to 3.3 volts. Oh, now I forgot completely. Okay, so before I copy those, because otherwise it's a pain in the butt, I will delete those other ones again. Now you will see why. So what we want to do before you copy those you want to also adjust the clearance settings. Clearance is 1.5. Minimum width of the traces is also 1.5 because this is the DRCs we are following. Anti-pad clearance is 1.5. And spoke width is something that has to be wider than the other settings because otherwise KiCad is complaining. Whatever. We set it to 2. So now, if I recreate it, it's much tighter. So it fills the layers tighter. Now we can duplicate it, and duplicate it. Edit, edit, F copper, and set it to backside, and F copper, edit, and put it on the inner copper, and then take the turn, duplicate, enter, edit, and put it in inner on 3.3 volts. Okay. B. Now let's see. Did the other layers ground, B copper. So because we don't have any vias that connect those together, we don't have any, the other ones don't enable. So let's just really quickly, for demonstration purposes, put in, this is history, select by browser, and I think I have it in pads, an SMD via, path through hole, SMD. Where do I have it? Is that in MISC? Oh yeah, it's a freestanding via. It's also fixed in the nightly builds now that you can just do via stitching. And net name will be GND. And build, now the layers are there. Very good. So we have top layer, it's red. Inner layer is yellow. And bottom layer is green. And now we need also the power layer. So we will put in another via. Okay. But we will set the pad onto the +3V3. And now the inner one is also filled. So just temporarily we will use it later, but we have now the connection so that the fills are shown. And now on the left, do not show filled areas or zones, so we can disable it. So we have it, but we don't see it, and the rat's nest will show that it is connected there. Okay. What next? Check, everything good. Yeah, so there we go. Okay, let's continue. We have the ground is connected here. So another interesting thing, this is now that I think about it. So another interesting thing that I found in one of the data sheets of the Cypress is USB connection. Now that I just remembered. And it says USB, let's do this. I think it said that you should connect the USB connection to ground, not directly, but through a resistor, to the shield. So instead of a ferrite, as we were discussing yesterday, it should be a resistor. There we go, I found it. So there is a resistor here. So they say VBus ground and shield, and it says connect the shield connection to ground through a resistor. This helps isolate it and reduces EMI RFI emissions. Keep this resistor close to the USB connector. Some experimentation may be necessary to obtain the correct value. It would be nice if they said what a good starting value would be, but okay. Let's just, I don't know, let's put that 2.7 k ohm resistor to ground. So instead of ground, this is the shield, vertical wire. Let's move this guy. And copy a resistor. Yeah, 2.7. Okay. Yeah, like this, whatever. Okay, now we have a resistor connected. Let's just generate the net, and it will annotate. Okay. The net, read current netlist, yes, close. So we have one more resistor somewhere, in theory. Where is it? Where are you, my resistor? It usually adds them. What did I do wrong? R10. Net, generate. Did I do something weird? Maybe I pressed cancel or instead of generating it or something. Net, read current netlist. Yes, please. There you go. There it is. And this will be connected to ground. So what we will do is create a zone around here that is a different priority than the one here, so that it pushes the other plane away. That's probably a good idea. Okay, so let's see. Priority level. I don't remember which way around the priority levels went. So let's just do this. And this will be net P1 pad GND. Let's call that net. Let's give the net a name. Wire, this, and call this. And now it has a name. And then generate the net. And read the net, read current netlist. Yeah, so shield. There we go. Okay, let's add this. Shield. Oh, wrong layer. We want it on the top layer. There we go. Better. Copper shield. Okay. The clearances are fine, so because it took over this defaults from the other one. Okay, so B. Let's see how this looks. So it is connecting. Then let's try to change this to, let's say, a higher level. Yeah, so now it is overriding. So it has precedence over the other one. We still have the thermals on here, so let's just make it smaller because this is not necessary. There we go. That's nice. So now we have the shield ground connected, and this can be just next to here. And we can just connect the trays together. Bam! It's connected. So now the shield is connected to ground through a resistor. Cool. What we still don't have is having ground connected. So let's just make a trace and see how that works. There we go. So that's connected to the plane. And then we can move this guy. This wants to be connected to 5 volts over here. Okay, we can hide this for now. Okay, do we want it this way or the other way? Yeah, let's just do this, and then we want 5 volts, like this. So that guy is connected. So these are short. I think we will make a differential pair out of these. This is something I rarely do. So we want to do I don't remember how this worked. Show microwave. Route, differential pair, unable to find complementary pair. Make sure the names of the nets belonging to the differential pair with _n, _p, or plus and minus. So we have to rename this net. Let's rename this. Oh, this would be is a good question. Can I rename the whole net? Tools. That's a good question. Let's see what Google says. KiCad rename net in schematic. How to change net names. Forum. This forum is very useful. I'm no new to KiCad. Place net name. Okay. Okay, I should look it up off the stream. If someone who is watching knows how it is done to change the whole net in the whole schematic in one go, please let me know. But yeah, it would be nice if that would be a thing. Find and replace, edit, find and replace, search for dp, replace with d _p. Let's call it USB DP. Find, replace, and okay. Replace, find. Okay, so this guy, I didn't mean to do this actually, but whatever. Okay, fine. This is actually correct. So let's move this guy away. I have to reorganize the schematic and clean it up so that it is less of a mess. It's at the moment a little bit janky. Okay, this and let's make some more space, move. And edit, find and replace, DM, and DM, find, replace, find, replace, find. The usability of this find and replace is not great unless I don't know the shortcuts for it. Probably are shortcuts on the keyboard, so that because it jumps the mouse immediately after you do a find or a replace, it's a little bit annoying. Okay, net generate, save, and then let's go here and net read current netlist. Yes, close. So this got renamed, so that's good. And then we have this also renamed. So now if we go on route differential pair, let's see. N, not minus, it's N. Annoying. Okay, find and replace. USB DM and replace it with N for negative. Find, replace, or replace all. There we go. Close. Save this. Net generate. Save. Net read current netlist. Yes. Close. Okay. So what happened now? Didn't do it. DN. Okay. Net generate save. Net read current netlist. This cycle of reloading netlists, just FYI, will also be gone. Will not be necessary. You still can export netlist in the nightly builds of KiCad, but you have one button synchronized to PCB button in Schematic, which makes it easier. So you don't have to always export the stupid file. Okay, so that now route differential pair. Let's try it again. The track width setting violates design rules. Okay. And where can I change this? And why is it route? Pair length. This is a measuring tool. Single track. This works. Differential pair. Current track width setting violates design rules. What? Design rules. Is there an extra setting somewhere for differential pairs? Yeah, you see that I'm not using the differential pair feature a lot. It would be good to know how to do this right. Like, how can it be wrong if it is correct? It's like, okay, well, I think I will leave it out and do some research because this is dumb. We could just wire it up to here. Anyways, but we have to do some more cleanup around here. So let me just move this. So these guys are, so this pin goes here, this one goes here. Can I route it between the paths? Yes, I can. So I could start here and then go this way and then this way and then this way. Or, yeah, if I was swapped them around, would that be an advantage? See, 7654. No, this is good because it is in the order that it is here. So they will be going in pretty much parallel. Yeah, Adding all this stuff will be fun anyways. I think I will put it onto the side, add a bunch of vias to pull it on the back side and untangle it and connect it to the protection stuff. Right, it will be interesting. Okay. Where were we? Yeah, so we can have this guy like this. Let's see how close we can get it to the connector, because then we can scoot everything to the side when we are doing these things. Okay, so then I would basically have these here on top above the traces like this, so that we can connect them over vias, split, 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 connect, connect, connect. Then this guy will be here doing the same thing, so nice even symmetric pattern. Then we could then how to do this? We probably will do a similar thing where we basically tap off the straight traces that go to the microcontroller and basically tap into the lines using vias from the backside. I think that might do the job. Okay, so this guy, let's try to just route it. 1, 2, 3, and 4, and 5, and 6, 7. It's complaining. Why is it? Yeah, it's jiggly wiggly. And there. Okay, cool. Now let's just adjust this, because there's there we go. So that's straighter. Yeah, this is where you have a footprint with imperial spacing against a metric design. It's a little bit iffy. We can have this so that it is using right angle, like 45 angles to escape from the pad. I like that better. And this guy too. Okay, cool. So these guys are connected. Bam. All right. Next, let's try to move this guy and see how this will work. B. So this would actually work like this. Do I want to so one like this and then up? Yeah, track near via. So we probably have to move this guy. Let's do this. Nope. Okay, let's try it again. Why is the design rule checker complaining? Oh, because it is too close to this track? Huh. Let's move it then. Let's do DRC, start DRC. Ah, that was it. It let me put the via there. Okay, whatever. The online DRC is not very consistent with the offline one. It's like they are slightly different from each other. But it is what it is. Okay. So we can have this like that. Then we can have this like this and connect it to the next track. Why did this move? What are you doing? Why are you doing this? Can you stop? Thanks. There we go. Start DRC. Will it complain? No. Okay. Okay. Yeah, I think if I just make connections like that, then we can see how this will look like later. There we go. So we have these. The question is, why is this one off and this one is not? Are these offset some weird way? Oh, they are. Interesting. So this guy is not on the middle line. This one is not on the middle line. That's what it was. Okay, let's redo this. Rip it up, rip it up. Okay. Okay. Yeah, these are not exactly on the grid here, so they are offset by 0.5 millimeters. Let's just switch grids. That's totally fine. Let's see if the vias will actually work in this way, and if I might need to adjust things. What about doing it this way? Yeah, okay. Then like this. What are you doing? There. Okay. Oh, the nice thing is it's yeah, it's exactly mirrored, so I can directly connect it. And let's try this. Let's go to the bottom layer. like this. Let's delete this. Yeah, and this guy, how far can you go? And via like this. Looks good. Yeah. Okay. There's still some garbage here. Let's redo this. Yeah, that looks good. We can also review this in 3D, just for the fun of it. Yay, very nice. This guy is missing a 3D model. This 3D model is offset by 90. We are missing models for these two guys. Yeah, this is why I'm saying I have to clean up my libraries, but because other designs have all the 3D models. Yeah, let me show you how this looks on the Blackmagic probe, for example. Like file, open recent. Magic probe, and if I go the 3D model, yeah, it has pretty much everything. Yeah, it's all set up correctly, but it's only in that model. Some of the changes have to be done in the footprints and stuff. Yeah, I should synchronize that stuff. This will be quite a project too, to clean this up. That's why the librarians are very useful, to have a bunch of people put together their efforts to make these things consistent with an attached but. Okay, so I have this done. This looks nice, and I will put this guy at the same distance. So where do we have this? How do I do this? Let's get it from the corner here, reset it here, and then check how far it is. It's -1.5. Let me write this down. Woo. -1.15, and then plus 1.4. 1.4. It's on the y-axis. So this will be -1.4 and -1.5, because it will go in the y-axis. Okay. So let me reset the relative distance here and move this. Stop it. -1.15, and then -1.4. Perfect. There we go. Now we can route this. 1, and then 2, we don't want it to interfere, and then this should be here. No, not via. Ooh, come on, keep going crazy. What happened? Oh, because this guy is in the way. That's what's happening. Yeah, that's the problem. Yeah, this guy has to be like this. Now we have enough space, or should have enough space. There we go. Yeah, so these guys have to be evenly spaced. There. There we go. That's correct. And we can do the same thing here. And move this guy too. Have it on the same level, so that the kinks are also all on the other side, so that this is all nice and parallel. Okay, that's nice and clean. This should go here. How far are we? 0.2. And then we can connect this guy here via. And then we need this guy. And via. There we go. Very nice. Yeah, this guy can be even adjusted. There we go. Nice. Okay. How does this look? Oh, we should. What is happening? Okay. Yeah. Nice straight traces and a few stitches on the back. And we have the pull-ups attached. Now we need to connect the protections. They can be pretty much very similar. So let's see. So we have PB1, PB0, PB2, PB3, PB1. Wait a second. So, yeah, I'm not sure I like that. It probably would be nicer this goes to ground. That would work. And 5 volts would connect here, but then we would want to connect PB0 to here, then maybe PB1 to here, then PB3 to here, and PB4 to here. What do you think? Yeah, that sounds good. So I can rewire this on the schematic. Oh, we can also connect these guys. Yeah, let's do that first. Reconnect, 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 and reconnect. Come on. Shove, please. Thank you. Thank you. Yeah, I love the push and shove. It's nice. Push and shove algorithm for the win. Yeah, it's a little bit kinky there, but okay. There we go. Very nice. So that's done. What is this complaining about? Oh, that's the via that was all over the damn place. Okay. That's sorted. Okay, so we want 1, 2, 3, 4. So rotate this way. So PB2, we want to be PB1. PB1, PB2, so move, 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 and move. Save, net, generate, save, net, read current netlist. Yes. Close. Yeah, that's looking good. Let's try this. Then we need places for vias here. So let's move this. And you are in my way. Move. 5, 6, 7, 8, 9, 10. Let's put it on this grid line. Then E took. Yeah, so right. The alternative would be to actually have this guy connect to the first trace, this guy connect to the second, this guy connect to the last one. Right. Because this is slightly silly. Right. Spiklevku would say rightio. Yeah, I think I have to think about it. I think we are also reaching the end of 2 hours. I think we will cut it here, and I might come back, but probably tomorrow, and get some more work done on this. I think we made quite decent progress. We started routing the board. I think it will be nice and neat. We will see. We have a lot of routing in front of us. We will spend quite a lot of time in here. I think it looks great, and I thank you for being here and watching what I'm doing. Please make sure to join the Gitter chat and ask questions if you have any. I will try to answer them as well as I can. If you have suggestions for the fx2grok circuit design, and you think I'm making some horrendous mistakes, please let me know. The datasheets are on the wiki of Sigrok. Also, I think it is great, the feedback I got from Uwe and from a lot of people from Micah Scott's chat, and suggestions from the Boltport Club people was really awesome. It was very useful. I think I made some good improvements. If you have questions, as I said, please add them to the chat. And if you have been, thank you for watching.